Hi, this video is about a puzzle game that me and two of my friends made over the past 2 months called Prove It for 3 Blue and Brown's annual Summer of Math Exposition event. The premise of the game is to build formal proofs. You are given a set of statements and must prove a different statement using rules of inference. Wire inputs according to specified patterns and get a corresponding output. The puzzles get pretty difficult, so this video is supposed to be a list of clues and solutions for the 38 levels currently in the game. If you think you would enjoy this game, give it a try and see if you learn anything new about formal proofs. You can play it for free on the itch.io page with no downloads required. If you get stuck, refer back to this video and the timestamps in the description can take you to the clue or solution for any level. The first few levels, however, don't have hints. There's nothing we can really reveal without just saying the solution outright, so clues start from level 19. With that preamble out of the way, let's begin. Level 0. Honestly, if you get stuck here, check your mouse. Maybe it's running out of battery or something. Level 1. This is where you're supposed to understand how rules and patterns work. The answer is the opposite of how you probably connected the wires first. Don't worry, you can select and delete connection wires or just override them. Level 2. Again, a very simple level. Just match the patterns in the OR introduction rule to prove the answer. Level 3. If you're confused by why there are two different rules for introducing the OR operator, look at the patterns. The order of inputs is very subtly different. Level 4. A hint of pattern matching may be required here. Level 5. We've already looked at adding the AND operator in level 0 and 1. In this level, we can remove it. If A and B is true, you can deduce that A is true and B is true individually as well. So we have two different tools for this. Level 6. The outputs of rules can be connected to inputs of other rules just as long as the patterns match. In this case, we have to eliminate the AND operator twice and build the answer back up from the 3 individually true statements. Level 7. Maybe if you're stuck on this one, jump back to level 1 and really try to understand how these rules work. You'll need it. Level 8. Another tutorial level, this time for assumptions. These will become very important, but later. Level 9. Assuming the goal directly won't work in any level. We have to build the same statement without using the assume rule. Level 10. Here we introduce the implication operator. You can read it as if A, then B. We also have a new implication elimination rule. Try to understand how it works, or just take a look at the journal. Level 11. This is just a chain of eliminating implications to get the output. Level 12. You're probably here to understand how assumptions are really useful. The idea is that you can assume certain propositions to be true and then use these assumptions for further inference rules. However, anything based on an assumption is poisoned. You can see that from the star before the expression as well as the orange highlight around the assumption as I hover over this expression here. To prove a statement, we want the final expression to not depend on any previous assumption. You can do this using special rules that use this orange circle connector. In this case, think about what implication introduction is doing. If I assume a proposition here, A is true, and then use that to prove A or B is true, then we can add the implication operator in between the two expressions, signifying the dependency. You can read this as if A is true, then the expression A or B is true. We clearly don't need to know whether A is actually true to show this implication, so the assumption just goes away. Level 13. This level is here to show you that an assumption can be used in both regular connectors as expressions as well as in orange connectors as their assumptions. Level 14. Building implies chains is simple. One thing to notice is that you have to assume the left-hand side of an implication to actually introduce that operator, even if you don't actually need to use that assumption for the second input of the implication introduction rule. This is just for consistency, nothing else. Level 15. This one is very similar to the last level, but reflexive instead. Notice how the assumption dependencies get eliminated here. I can use the assumption in both the orange connector as well as the regular connector. Level 16. Let's understand contradictions. Contradictions are closely related to the not operator. If a proposition is true, the not of that proposition must be false. But what happens when we somehow prove a proposition P and a not of that proposition P to both be true? Well, this is a case of contradiction, which is denoted by a special keyword false. When we reduce false is true, it indicates that our system is not consistent, and some claims, some assumptions that you probably made, or some givens contradict each other. Level 17. Proving a contradiction isn't a special one-off thing. It's actually useful. In this case, you can explode all known logic. Essentially, if some statement is both true and false, any proposition is automatically true. Level 18. Here's another way to remove assumption dependencies, the not operator. If you assume some proposition to be true and go on to show that this causes a contradiction, then the not of that proposition has to be true. Simple enough when you verbalize the logic like this, right? Level 19. From here on out, we'll start giving clues if you get stuck. This is a real filter level. Don't be discouraged if you get stuck. Try to verbalize the rules and what you actually need to do. If you're still stuck, there's a few hints that you can use. Hint 1. Try to think about what necessarily needs to happen. In this case, the goal contains the implication operator, which means you need to use the implication introduction rule. Try following through with that logic and see other forcing moves. Hint 2. What do you think happens when we make two contradicting assumptions? A is true and not A is true. Hint 3. The explosion rule is a red herring here. Try to use not introduction on not A is true. Here's the solution. As mentioned in the first hint, we have to start by assuming A is true and using that statement as the LHS of the implication introduction rule. Now, to prove not A is true from the assumption A is true, we have to do a not introduction on not A is true. To do this, first assume not A is true. Show that the two assumptions are contradictory and use this contradiction to add the not operator to not A is true. Then finally just wire the knot into the implication introduction. Level 20. Hint. As usual, start by looking at forcing moves. We have not be implies in our goal. So we need implication introduction and an assumption of not be is true. Now, under this assumption, try to assume A is true and see if that leads to a contradiction. The solution starts at the hint again. Assume not B and use it as the first input of implies introduction. The second input has to be not A is true, which can be done by assuming A is true, showing that there is a contradiction due to the given implication and our previous assumption, and then using not introduction. Level 21. If you start from absurd statements, you can deduce absurd statements. The hint here is that B and not B might be an absurd assertion, but it is a valid proposition. You've already seen a rule that can prove anything under certain conditions. Can you do the same but using some assumption? Here's the solution. As usual, if you try to check forcing moves, you see that you have to start by assuming A and not A is true. Then, using both the and left and right rules, show that this is a contradiction. And finally, use the explosion rule to prove B and not B is true. The last step is using implication introduction as usual. Level 22. You may be here to see what OR elimination actually is. It might be a bit weird looking, but it makes intuitive sense if you verbalize it. The idea is that you don't know which side of the OR expression is true. So to get rid of the OR, you have to show that a certain other statement is true regardless of which side of the OR is true. This is what the first and last inputs to the rule are. You are trying to prove a certain third statement if the left of the OR is true, and you're trying to prove the same third statement if the right of the OR is true. Level 23. Hint 1. Sort out the given statements and notice that you have to prove A implies P and B implies P and use OR elimination. Also recall that for the implies introduction rule, you have to start by assuming. Hint 2. Refer to level 22 to understand what OR elimination does if you are stuck here. Here's the solution. It's very asymmetric. We have an expression stating A or B is true. So we have to prove P is true regardless of which of these is true. To do this, B implies P is already given. We just have to construct A implies P is true from the two given statements. We have done something similar before. Start by assuming A, eliminate a couple of implications, introduce the implication back. Then plug everything into OR elimination and you have your proof. Level 24. Here's the first hint. Just like we proved AND symmetry in level 5, we have to eliminate OR here to prove our goal directly. The second hint is to not forget that for implies introduction to work, you have to start by assuming. You also need to construct two implications, one for the left of the OR and one for the right of the OR. Here's the solution. In this level, we have to use OR elimination to prove our goal directly. On the left, we just have to construct the statement A implies B or A is true. To do this, assume A is true, then use OR right to prove B or A is true. Then add the implication. On the right is the similar story. We have to construct B implies B or A is true. Assume B is true, use OR left to prove B or A is true, and then finally plug it all into OR elimination. This pattern of assuming both sides of the OR to prove an assertion is going to recur in future levels as well. So make sure you understand it by verbalizing it. Level 25. This level shows how the OR operator distributes over the AND operator. Here's the hint. Notice that the OR operator is at the top level of the expression. This means that whatever we do, we have to use OR elimination here first. Try figuring out if you can prove the goal from both sides of the given OR. Here's the solution. Like the hint suggests, use OR elimination. We have to prove our goal statement by proving that A implies the goal is true and B and C implies the goal is true. So, on the left, assume A is true and then construct the goal using the usual AND and OR introduction rules. The right is fairly similar. Assume B and C is true, eliminate the AND to get B is true and C is true, then construct the goal expression in the same way. Finally, add the implication and plug everything into OR elimination. It can seem a bit tedious, but that's just how formal proofs are. Level 26. This is the inverse of the previous level. Notice that the AND operator is at the top level of the expression. This means that whatever we do, we have to use AND left and AND right here. Here's the solution. The trick is similar to the last level, but first eliminate the AND operator. Now use OR elimination on the AND right output to prove our goal. Even if B or C is true, we have to prove the goal is true. So on the left, we have to have B implies the goal is true, and on the right, we have to have C implies the goal is true. So for the left side, assume B is true, then use simple AND and OR introduction rules to get the goal, and then add the implication in at the end. And the right is the same story. Assume C, use the basic rules to create the goal, and then add the implication. Fairly straightforward, if a bit tedious, but that's fine. Level 27. This level shows that OR is associative. The hint is that you will have to eliminate the given two ORs and introduce a few ORs in the solution. You have to do that in the correct order though. You can figure that out. Here's the solution. This is another tedious level, but it's to make sure you really understand what you need to do. At the highest level, we need to eliminate OR to prove the goal. The right side of this OR elimination is simple. Assume C and use the simple OR introduction rules to create the goal. The left-hand side is a bit more interesting. We need to prove that A or B implies the goal. So we start by constructing A or B is a prop, assume that to be true, and then use the OR elimination on that assumption. For this second OR elimination, we have to do the same thing as we did for the C side of the first OR elimination, but using A is true and B is true instead. So on the left, assume A is true, build up the goal using OR introduction, and add the implication. On the right, assume B is true, build up the goal using OR introduction again. The final step is just putting it all into the two OR eliminations. Level 28. To prove A implies B, you can start by assuming A is true and see where that takes you. You may have to use some OR elimination here. Here's the solution. There are multiple ways to prove this, but here's the most simple way. We definitely have to assume A is true to add the implication required in the goal. Then we start with OR elimination again, and this time we are trying to prove B is true based on either side of the OR, so that we can use it in implication introduction. On the right, we just need to show that A and B implies B, which is fairly simple. Assume A and B is true and use AND right to eliminate the AND operator. The left side seems a bit trickier. We have to show that not A implies B is true. We have to assume not A is true, of course, and then use contradiction with our first A is true assumption to show that this can never happen. Then use the explosion rule to prove B. Try to understand why this works. We are saying that for our goal to be true, we can never assume not A is true. The final step is just plugging everything into OR elimination and then putting the output of the OR elimination into the implication introduction rule. Level 29. Here's the hint. To prove A implies B, you have to start by assuming A is true. So to prove A or C implies something, you'll have to start by assuming A or C is true. Beyond that, you can probably figure out what to do based on the rules that you have been given. Here's the solution. As usual, referring to the goal, we have to add an implication by first assuming A or C is true. The trick is to use OR elimination on this assumption to prove B or C is true, regardless of whether A is true or C is true. The right side is simple. We just have to prove C implies B or C is true. So assume C, use the OR right rule to create the statement, and then use implies introduction. On the left, we have to prove A implies B or C is true. To do this, we'll use the given implication. Assume A, then eliminate the implication to get B is true. After that, use OR left to create our desired statement. Then use implies introduction. Putting it all together into OR elimination isn't the end though. We'll have to add the final implication to remove the final assumption dependency. Level 30. Okay, time to understand what this new rule is. The law of excluded middle states that for any proposition, either itself or its not is true. This rule is usually used in tandem with OR elimination to show that it doesn't matter whether a proposition is true or false. You can prove a certain statement either way. Level 31. Here's the hint. If you're naturally gravitating towards assuming A is true to use implies elimination, you're on the right track, but that's not the main part of the proof. You have to use the law of excluded middle here on a certain proposition along with OR elimination. Here's the solution. This level is a very specific archetype of level relevant to the law of excluded middle. In this case, you can use the EM rule on A is prop. Notice what we have as our goal is either not A is true or B is true. In the output of the EM rule, if A is true, then using the given implication, we can prove that B is true. If not A is true, then the goal is directly true due to the OR operator. So to do this, on the left, assume A and use implies elimination to get B is true. Then create the goal statement and add the implication in. On the right, assume not A is true, then directly create the goal statement and add the implication in. Plug everything into the OR elimination to get the answer. Level 32. We are proving pretty complicated statements now. You might be wondering how to prove this without using not introduction. Well, there is a way. Here's the hint. You can use the law of excluded middle on A is prop to prove not A true. Explosion could be helpful. Could you try doing the same on B is prop? Here's the solution. As the hint suggests, you use two EM rules to build the two parts of the goal. For proving not A is true, use EM on A is prop with OR elimination. For the right side of this OR elimination, assume not A is true, add a reflexive implication, and you're done. But for the left part, you might be wondering how can A imply not A is true? Well, let's assume A is true first and look at our given statement. If A is true, then A or B is true, which contradicts with the given statement. which means that we can use the explosion rule to prove that not A is true. Add in the implication and fill out or elimination to get not A is true. A similar procedure works for proving not B is true. On the right, we have another reflexive implication, and on the left, we have to explode not B is true into existence. Now that we have our two parts of the goal, just put them together with a single rule. Level 33. Here's the other direction for De Morgan's law. Here's a hint. Assume A and B is true, then check if it contradicts with the given assertion. Here's the solution. As the hint suggests, assume A and B is true and eliminate the and to get A is true and B is true. Now we can use these on either side of an OR elimination to generate contradictions. To do this, of course, we'll assume not A and not B, then add the implications and connect them to the OR elimination rule. Now we can use this contradiction from the OR elimination rule to add the not operator to our initial A and B is true assumption to get the answer. Level 34. Try to understand the given assertion. It is trying to say that if we assume not A is true, then we encounter a contradiction, resulting in false is true. What we want to conclude is that since not A leads to a contradiction, A must be true. Here's the hint. The starting point is using EM on a prop and not the given statement. The solution is fairly simple from the hint. Use EM on A's prop and put that into OR elimination. The left side of the OR elimination is simply a reflexive implication. So just assume A is true and add the operator in. On the right side, assume not A is true and then use the given statement to get a contradiction. Then use that to explode A is true into reality. Finally, plug all the implications into the OR elimination rule to get the result. Level 35. Here's the hint. The starting point is using EM on a prop and not the given statement. Here's the solution. As the hint suggests, start by using EM on A's prop with OR elimination. On the left side is a reflexive implication, so assume A is true and add the implication operator. On the right, we can assume not A is true, then use the given to prove a contradiction. Then explode A is true into existence, add the implication, and plug it into OR elimination to get the final proof. Level 36. Here's the hint. Recall how to deduce not A from A. This was done in level 19. Here's the solution. This time, again, since we are not really proving anything contradictory, the explosion rule is a red herring. We start by assuming A is true and putting that as the first input of not introduction. We have to prove a contradiction between A is true and the given not A is true statements. To do this, first, we assume not A is true. Show that this is a contradiction and add a not to the second assumption, basically showing that not A is true if A is true. This is level 19. Then use this output to contradict with not A is true. This will give you the final false is true statement that should be used in the final not introduction rule. Level 37. Here's the hint. You have A's prop and B's prop. One of them you'll have to assume to be true, and you have to use the EM rule on the other. Here's the solution. The answer to the hint can be derived by looking at the forcing moves again. Since we need to have A implies B as the output, we necessarily need to assume A and then use EM on B with OR elimination. The OR elimination can be used to prove B is true with the help of the A is true assumption, and then remove that dependency using implies introduction to get the answer. So the left of the OR elimination is a simple reflexive implication for B is true. Assume B is true and use the implies introduction rule directly. The right side is more involved though. We have to assume not B is true and use implies elimination to prove not A is true. Well, this new statement contradicts with our initial A is true assumption, so we can explode B is true into existence. Now we just add the implication in and finish out the OR elimination to get our proof. Level 38. This level is about Peirce's law, but in a weird way. Here's the first hint. The starting point is using EM on a prop and not the given statement. Here's the second hint. You can make contradictory assumptions. Here's the third hint. You never need to assume B is true. Here's the solution. We have to start with the EM rule on A is prop, using OR elimination as usual. The left of the OR elimination is a reflexive implication. A implies A. On the right side, we have to assume that not A is true for implication introduction. But the trick is to also assume A is true. Of course, this is a contradiction, so you can use this to explode B is true into existence. Rather than assuming B is true for getting A implies B, use A implies B to eliminate implication from the given to get A is true. Then finally add the final implication for proving not A implies A. Then just plug it into the OR elimination to get the answer. And that's that. No large outro this time because there's nothing to say other than hope you enjoyed the game and learned something about proofs and zero order logic. See you next time.